we're going to go over here some questions on finding the least common multiple that we use as part of a process for some various algebra techniques like adding unlike fractions or work with complex fractions or solving rational equations. So the technique we went over in class depended heavily on our knowledge of prime numbers, our prime factors, right? The primes here are the building blocks of numbers, and these are numbers that only have 1 and themselves as divisors. 2 here is the smallest prime. 1's not a prime's bigger than 1, and 2 is the first prime, it's the only even prime. The next prime will be 3, 5, 7, 11, 13, 17, 19, 23, and this is the beginnings of our primes. This list goes on forever. There's infinitely many primes. And we talked about this in class. We went over this. We also talked about the fact that terms can be thought of as primes as well, meaning building blocks. A variable x to the first power, or just x, is thought of as being prime because primes are also known as being, aka, simply not factorable. So the variable y is prime, not factorable. Z is prime, not factorable, any variable. We can also look at expressions that are not factorable, like x plus 1, x minus 1, maybe 2x plus 3, 3x minus 4. Any expression as well that's not factorable, and we see that here, these are thought of as being prime. So we discussed this in class, and we're now going to use this again. And we're going to use this in our technique where we have to find the least common multiple of 15 and 36. So we need a prime number here that will divide at least 2 of these numbers, and since there's only 2 numbers, it has to divide both. So we go through our prime list and we discover that 3 goes into 15 5 times. That is, 15 divided by 3 is 5. 3 goes into 36 as well. We know 36 divided by 3 is 12, so we put the 12 down here. So the prime 3 divides both of these terms, and what you guys see here again is the answer, the quotients go here. So this is how we started finding our primes, or I should say the least common multiple for various numbers. We use the primes, and now we repeat the process if possible. We got to find a prime, a number up here, right? One of these numbers or one of these terms. It's going to be a number because we have numbers 5 and 12 that divide both of these numbers. Remember, 1 is not prime, so you might try 2. 2 divides the 12, but it does not divide the 5. So if you can't find a prime that divides both of these numbers, that means you're done, so that the LCM here will be 3 times 5 times 12. And you could say the LCM will be 15 times 12. Now 15 times 12 is going to be 2 times 5 is 10, 2 plus 1 is 3, 5 and 1, you get 0, 8, 1, so your LCM here will be 180. This is what we're going to use, and this is what the answer is. So this is how we answer the first question, finding the least common multiple of 15 and 36. Number 3, the LCM of 3 and 27. So again, we need a prime that goes into both of these numbers. 3 goes into both. Now 3 goes into that first 3 once. 3 goes into 27 9 times. So at this point, we try to see if we can repeat the process. Is there a prime that goes into both 1 and 9? The answer is no. Don't say 1 because 1 is not prime. Since we can't find a prime that goes into both, we're done. The LCM will be 3 times 1 times 9, or we say the LCM here is 27. Number 5. 5 and 11. We need the LCM of 5 and 11. We need a prime that goes into both of these numbers. And we'll find that there is none, so that means we're done. My LCM will be 5 times 11, or the LCM here is 55. Now I want to notice something here, or point something out, that both of these numbers are prime. And so since they're both prime, it makes sense that there is no other number, since primes are building blocks, that could go into either of them. So the LCM is always going to be, when you have a set of prime numbers, is simply going to be the product of those two. So that might be something that's very useful for us in the future. We have to remember this. We just multiply when they're both prime. 6, 12, and 4. So we need the LCM here of 6, 12, and 4. We need a prime that goes into at least 2 of these numbers, 2 or more. At least 2 means 2 or more. So 2 goes into 6 3 times. That's the quotient. We found that. 2 goes into 12 6 times. And 2 goes into 4 twice. So the prime 2 goes into all 3 of the numbers. We just need it to go into at least 2. Now we can repeat the process here. We again need a prime that goes into at least 2 of these numbers. And in this case, a couple of primes will work, and it doesn't matter which prime you use. You can use 3 or you can use 2. So at this point, let's use 3. And we know 3 goes into 3 once. 3 goes into 6 twice. But 3 does not go into 2. So we just bring down the 2. If it doesn't divide the number, just bring it down. So the prime went into 2 of the numbers, and that's good enough. And at this point, we get to repeat this process yet again. We need a prime that goes into at least 2 of the numbers. 2 we can use because it goes into both of these numbers. It goes into 2. Once. 2 does not go into 1, so we just bring it down. Since we can't find another prime that goes into at least 2 of the numbers, don't forget 1 is not prime, it means we're done. So the LCM here is going to be 2 times 3 times 2 times 1 times 1 times 1. Or we can say that the LCM is going to be 12. Nine, 4, and 1. We need a prime that goes into at least 2 of these numbers. And we find that there is none. Remember, 1 is not prime. 2 goes into 4, but it only goes into exactly 1 number. There are 2 numbers here. So the prime we need has to go into both of these numbers because it has to go into at least 2 numbers that you have in your original list. If you only have 2, it has to go into both. There is none, so that means that we just simply multiply 4 with 1, and our LCM here is 4. Number 11, 15, 10, and 6. So we need a prime that goes into at least 2 of these numbers. 5 goes into 15 3 times, that's the quotient. 5 goes into 10 twice, that's the quotient. 5 does not go into 6, so we bring it down. And we see that we can repeat this process. We need a prime that goes into at least 2 of these numbers. 3 goes into 3 once. 3 does not go into 2, so we bring it down. 3 goes into 6 twice. And we see we can repeat this process. The prime 2 doesn't go into 1, we bring it down. It goes into 2 once. It goes into 2 once again. And we're done. Your LCM will be 5 times 3 times 2 times that 1 times 1 times 1, or simply the LCM is 5 times 3 times 2. LCM will be here 30, since that's what 5 times 3 times 2 is. 30 is the least common multiple. $13, $18, $12, and $20. We have 3 terms here. We need a prime that goes into at least 2 of these numbers. 2 goes into 18, 9 times, I gave the answer. 2 goes into 12, 6 times, that's the quotient again. 2 goes into 20, 10 times, here's my quotient. And again, this 2 prime happened to go into all 3, we just needed to go into at least 2. Since we can repeat the process as there is another prime that will go into at least 2 of these numbers here, the 9, 6, and the 10. 3 goes into 9 3 times, 3 goes into 6 twice, 3 does not go into 10, so we bring it down. And then we check this list, and we see that the prime 2 can go into at least 2 of these numbers. 2 goes into 2 once, 2 goes into 10 5 times, 2 does not go into 3 with a 0 remainder, so we bring it down. And at this point, we have to double check to see, let's put our check marks there just to double check here. We want to see whether or not a prime could go into at least 2 of these numbers that are left here, 3, 1, and 5, and we find that there is none, so that means we're done. Our LCM will be 2 times 3 times 2 times 3 times 1 times 5, so this is going to be some multiplication here. So that LCM will be, if we look at this as 6 times 5, and we know that 6 times 6 is 36. 36 times 5, we're going to bring out our multiplication algorithm because you can never get enough arithmetic. 5 times 6 is 30. 5 times 3 is 15, plus 3 is 18. So my LCM here will be 180. And there you go. $5, $30, and $15. We need a prime that goes into at least 2 of these numbers, meaning 2 or more. The prime 5 goes into 5 once, 5 goes into 30 6 times, 5 goes into 15 3 times. We need a prime that goes into at least 2 of these numbers. 3 doesn't go into 1, so we bring it down. 3 goes into 6 2 times. 3 goes into 3 once. Here you go. Let's multiply all these numbers. So my LCM will be 30. 16, 4, and 12. 16, 4, and 12. We need a prime that goes into at least 2 of these numbers. 2 goes into 16 8 times, 2 goes into 4 twice, 2 goes into 12 6 times. We can repeat the process because, again, we need a prime that goes into at least 2 of these numbers. 2 goes into 8 4 times, 2 goes into 2 once, 2 goes into 6 3 times. And at this point, we notice that we can't find a prime that goes into at least 2 of these numbers, so that means we're done. So my LCM here will be 2 times 2 times 4 times 1 times 3. My LCM becomes 4 times 4 times 3, which is 4 times 4 will be 16 times 3, so the LCM here will be 48. X and x squared. Okay. So let's discuss this a little bit again because we get to repeat our process here, this time for variables or terms. And remember we had a list of primes here, right? Our primes can include variables like x, y, z, as long as these variables here, or these terms, are not factorable. Even x squared plus x plus 1 is thought of as being prime simply because it is not factorable. So let's remind you guys here. If you can't factor, it's not factorable, it's thought of as being prime. Now, again, we need a prime here, one of these kinds of terms that you see here in this list that will divide both of these. And the first term here is x. So here's what we're saying here. We're going to use some algebra here. This first x is a numerator. The second x is the denominator. So x divided by x is in fact 1. So we have a quotient that does not have a remainder, or the remainder is 0. This is what we mean by divides. X squared is also divisible by x, again by properties of exponents from beginning algebra. And the quotient again here is x. So we see that we need a prime again that will go into at least 2 of these numbers, and we actually can't find one because 1 is not prime, and x does not go into 1. X goes into x, but not 1. So this means we are done, and our LCM here will be x times 1 times x, or simply the LCM here is x squared. Now, remember what we mentioned in class here, because we have a fact here. We can always find the LCM of these denominators because the LCM will be, if they give us 2 variables with different powers or even the same, the LCM will always be x to the largest power, meaning whatever power is larger for n and m. So in this example, if they said, what's the LCM of x and x squared? Well, remember, x just has a power of 1, and so we have to compare now 1 versus 2, the power, and determine which one is in fact larger. So the 2 is larger, that means x squared is our LCM. And that's actually what we got right up here. So ladies and gentlemen, again, just as a reminder here, there's a couple of ways to go about this. It's up to you. We could go about it the same way we've been doing so, or we could use the fact, whichever you like. X to the fourth. Now, if we try to go about it the way we've been going about these, we need a prime. X works. That goes into both of these. So x divided by x is 1. X to the fourth divided by x is x cubed. Because you're doing, again, division, you're really using properties of exponents. And these are my quotients here, which go on this side. So this is the most common question people ask. And also we notice that we can't repeat the process because we need a prime again that goes into both of these. One is not prime. And so all we have to do now is multiply x times 1 times x cubed, and that LCM will be x to the fourth. So you're done. Now notice, could we have used the fact here? Compare the powers. Which power is larger, 1 or 4? And you'll find it's 4 here. So the LCM is x to the fourth. X squared and x cubed. So if we repeat the process by using a prime that goes into both of these, you can't tell me that x squared is prime. It's not. But we know x is prime. Now, x squared divided by x is just x. We put the quotient here. X cubed divided by x is x squared, x cubed over x. This is where our quotients go. And again, we can repeat the process because we know that the prime x will divide x once. X squared divided by x is just x. And now we're done. And so your LCM will be, again, by taking x times 1 times x, or simply x cubed is the LCM. Now let's think about the fact. It would be easier to use the fact here because the largest power is, in fact, the x cubed, as we see over here. So I think at this point, I'm going to simply use, whenever I see this, I'm going to use the fact. I just compare my powers. 6 versus 2. Which one is larger? The LCM will be x to the 6. Number 27. In 27, we have 3 terms now, x to the third power, x to the fifth power. Now, this process can be generalized. We need to determine the largest power again. 1, 3, 5. So the LCM here will be x to the largest power. In this case, it's 5. This is the simplest way to go about this for questions that involve the same variables. 29, you have 6x and 2x. Now, the strategy is going to be this here. What you're going to do is you're going to find the LCM of the numbers 6 and 2 separate from your letters, or your variable here, x. So we need a prime that goes into 6 and 2. 2 goes into 6 3 times. 2 goes into 2 once. We can't repeat the process, so the LCM here will be 2 times 3 times 1, or the LCM here is 6. For the variables, first power. The LCM will be x to the first power, since 1 is the largest by default. So altogether now, for your final answer, 6x, you get now what? 6x. And you're done. (31) 4x, 10x. We need the LCM of the numbers separate from our letters here. So, by process, again, 4 and 10. A prime that goes into both of these is 2. 2 goes into 4 twice. 2 goes into 10 5 times. We find that we can't repeat the process because we need a prime number that goes into both 2 and 5, and there is none. So our final answer is going to be 2 times 2 times 5 for the numbers, or simply 20. For the letters, x to the first, x to the first. The LCM is x to the first. So your final answer is going to be 20x, because it's 20 for the numbers, x for the variable, or variables. Final answer is 20x. (33) 5x, 8x squared. 5 and 8, x and x squared. Do them separate. I need a prime that goes into 5 and 8. I find that there is none. So the LCM here is going to be 5 times 8. LCM here is 40. For your variables, x to the first power, x to the second power. LCM is x squared. So since we do the numbers separate from the variables, 40 and x squared, final answer will be 40x squared. Here's our LCM. (35) 15x squared, 2x cubed. The numbers separate from the variables. The LCM of 15 and 2, we have to have a prime that goes into both of these numbers. We see that there is no primes that will go into both. So we're done. The LCM will be 15 times 2. For the numbers, it's 30. We just need x to the largest power. So for the variables, it's going to be x to the third power, since 3 is largest. 30 x cubed. LCM will be 30x cubed. the numbers separate from the variables. $37 is interesting. 6, 12x, 3x squared. Now when we see this and we say things like, do the numbers 6, 12, and 3 separate from the variables, you have x squared here, and you may notice that there's absent an x to a power here. What you can do is put x to the 0 power, because x to the 0 power is 1. So this is 6 times 1, which would be 6. So now we can truly say, do the numbers 6, 12, and 3 separate from your variables. Now give me a prime, right? We need a prime that goes into at least 2 of these numbers. So we can say 2 goes into 6, 3 times, 2 goes into 12, 6 times, 2 doesn't go into 3, bring it down. Give me a prime that goes into now at least 2 of these numbers. Well, 3 goes into 3 once, 3 goes into 6 twice, 3 goes into 3 once. There are no other primes. So for the numbers, LCM is 2 times 3 times 1 times 2 times 1. My LCM will be 12. Now for your variables, the LCM is x to the largest power now. So let's compare our powers here. 0, 1, and 2. We find that 2 is the largest. So for the variables, the LCM is x squared. Our final answer is going to be 12x squared, because for the numbers it's 12. For the variables it's x squared. Final answer is 12x squared. $39. 5, 10x squared, x cubed. This question is very similar to the last one with a few exceptions here. So if you notice here, we want to do them separate. The numbers 5, 10, a number is missing here. Put a 1. So 5, 10, and 1, we're going to have to find that LCM. For the variables here, something's missing there. We got x squared, we got x cubed. Fill this in with x to the 0, which is 1, because 5 times 1 is 5. So find the LCM for the numbers. A prime 5, or the prime 5, goes into both of these terms. We need a prime that goes into at least 2. 5 goes into 5 once. 5 goes into 10 twice. 5 does not go into 1, so we bring it down. We repeat the process, or at least we try to, when we find that there is no prime that goes into at least 2 of these numbers, because 1 is not prime. LCM. 5 times 1 times 2 times 1. The LCM will be 10 for the numbers. For your variables, it's x to the largest power. 0, 2, and 3, and we find the largest here is 3. So together, for the numbers and the letters, LCM for the numbers is 10. For the variable, it's x to the third power. This is 10x cubed. And you're done. $41. 11x, 22. Find the LCM of the numbers separate from the variables. And again, you notice a term's missing. Replace it with x to the 0, which is really 1. So now we can find 11 and 22. We find the LCM of those two. Well, we need a prime. We need the LCM of 11 and 22. We need a prime that divides both of those numbers with a 0 remainder. 11's prime goes into 11 once, goes into 22 twice. We need a prime that goes into at least two of these numbers, or both of these numbers, and we find that there is none. So the LCM will be 11 times 2. Doing the arithmetic, 11 times 11 is 121 times 2. So my LCM here is going to be 242 for the numbers. For the variable, or for the letters, the LCM will be x to the largest power, 0 or 1, and we find 1 is the largest power. So your final answer here for this question is going to be 242x to the first power, because for the numbers it's 242. For the variable, it's x to the first, which is just x. So your final answer is 242x. Here's my LCM. (43) 5x and 2y. Again, the numbers separate from the letters. We need the LCM of the numbers, 5 and 2. We need a prime that goes into both of these with a 0 remainder. And the answer is that there is none. So for the numbers, the LCM will be 5 times 2, which is 10. Now, we have an interesting situation. I want you guys to remember that primes, again, are the building blocks of numbers. For the expressions of the variables, x and y, and z, and then the others are considered prime if they're not factorable. So we have x plus 3, and we can have y minus 7, and we can have x squared plus 5, or we can have x squared plus x minus 1. These are all, again, terms that are not factorable. And so if I want to find the LCM here of x and y, I want you guys to consider this here. We're going to go through the procedure here. We need a prime that goes into both of these numbers. It has to go into both, and we find that there isn't any. So like before here, the LCM here is the product. It's going to be xy here for the variables, but I want to point out, just like before, when both of these numbers here are prime, even if they're variables or expressions, then the LCM will just be the product of them. It's going to be x times y. So now all together here, since the LCM of the numbers is 10, and for the variables it's xy, your LCM here is going to be, as a final answer, 10xy. It's the product here. But this is a very good example that's going to show up very often for us. We talked about this in class, and we're going to see this quite often. So I want you guys to know that maybe this picture here, again, x is prime, y is prime, the LCM will be the product here. This is what we're saying again. That's something that's going to be used over and over. So let's see what happens with the next questions and how we use this. 45. 6xy and 4y. Now I'm going to say a few things here. We're going to do them separate. The number 6 separate from the variable x. And you say, well, there is no x over here. We can put one. And that's going to be separate from the y variable. So I can sneak in here x to the 0 because my power for y and this x over here is 1. So now I could do these things separately, one at a time. So we need the LCM of the numbers again, 6 and 4. The prime 2 goes into 6 3 times. The prime 2 goes into 4 twice. Because again, we need a prime that goes into both of these numbers. And we try to repeat the process and we find that we can't. So that means we're done finding the LCM for the numbers. So my LCM for the numbers will be 2 times 3 times 2 are simply 12. Now we need the LCM for the variable x. So if we take a look at this, x to the first times x to the 0. So for the variable x, it's x to the first. We also need to find the LCM for the y variable. And we compare 1 and 1. The largest power here is going to be 1. So the LCM is y to the first. So remember, we simply do these separate, one at a time. Now, the final answer is going to be, you're going to take the 12, x, and y. For the numbers, it was 12. For the x variable was x to the first, which is x. For the y variable, it's y to the first, which is y. So your final answer is going to be 12xy. Here's your LCM. Number 47. Nine x squared, 4y, and 2. Now this is going to be interesting for a few reasons. 9, 4, and 2 are for the numbers. We have the x variable, and over here we're absent an x variable, so we're going to put x to the 0. And I'm going to remark here that, let's undo that. Let's change the size of our eraser. I'm going to remark here that we are also absent an x variable here as well. So we can put, again, x to the 0. So that you can notice that we find the LCM for the x variable separate from the y variable. Now we're also missing here a y variable. It's not missing over here, so we have that third variable here, or the third term. And again, there is no y here, so we can put y to the 0. So for my LCM of the numbers now, we have 9, 4, and 2. We need a prime now that goes into at least 2 of these numbers. Now 2 doesn't go into 9, but 2 goes into 4 twice. 2 goes into 2 once. 2 doesn't go into 9, so we bring it down. we try to repeat the process. We need a prime that goes into at least two of these numbers. We find that there isn't any. So that your LCM will be 2 times 9 times 2 times 1, or the LCM will be 18 times 2, which is 36. That's my LCM. For the x variable, we need x to the largest power. 2, 0, 0, it's x squared. For the y variable, 0, 1, and 0, it's going to be 1. So altogether, my LCM will be, take the numbers, 36, x squared, y, 36x squared y. That's your final answer. Here's my LCM. Now, I want to remark here that there's an easier way to do this here as well. So I'm going to say, let's maybe think of this as well. Let's note, for the variables here. Back in this original question here. So let's go back here. Another way to look at this kind of question, again, is to separate the numbers like we did. And we find the LCM of 9, a 4, and 2. We find that the LCM is 36. Now, for the variables here, we could just simply say and notice that we have an x squared and we have a y. So if we want to repeat that process again, x squared, y here. We need a prime that goes into both of these. And you say, well, x goes into x squared, but it doesn't go into y. Y goes into y, but it doesn't go into x squared. What I'm remarking here is that there is no prime that goes into x squared and y. And so, ladies and gentlemen, you're done. So for the variables, we could just say our LCM is going to be the product here. It's simply x squared y. And so notice, we don't have to now go through the work that we just did separately for the x variable and for the y variable. We could have done this work and said that the LCM for the variables is simply x squared y, and then as a final answer, we get the same again, 36 x squared y. So we can also go and use the technique here if we understand what it means not to be, factorable or prime for variables or for expressions or terms. It's simply not factorable. So that knowledge is useful here, and it could make this work now very easy. So we don't have to always do them separate the way we've been doing that, and I'm going to try to do some where we don't. So we can say here's 12 xy, and then here is 8y squared. Let's try this technique again. Again, do them separate. Numbers from the variables. 12 and 8. So give me your prime that goes into both of these numbers. 2 goes into 12 6 times. 2 goes into 8 4 times. Give me a prime that goes into two of these numbers. 2 goes into 6 3 times, and 2 goes into 4 twice. We need the LCM. 2 times 2 times 3 times 2, because we can't repeat the process. There is no prime that goes into both of these. So for the numbers, my LCM is going to be 4 times 6, which is 24. This is for the numbers now. Now let's consider the variables here. I mean xy and y squared. So we're going to focus on these variables with the same technique. xy and y squared. We need a prime here that goes into both of these. What stands out to me is y. The prime y will go into both. Now here's what we mean. xy divided by y is x. Y squared divided by y is y. So the quotient here, which is what your answers are, they always go down here. This division is x, or this quotient is x, and this quotient is y. So again, we need a prime that goes into both of these, and we find that there is none. So the LCM for your variables are going to be y times x times y, or simply the LCM will be xy squared. So as a final answer here, for the numbers it's 24, for the variables it's xy squared. So this will be 24 xy squared as a final answer. This is how we use the technique with variables. Now, some students, again, may say, I think I like to compare powers, xy versus x to the 0, y squared, because there is no x variable there. And again, the answer is going to be x, y to the largest power. So we get to compare for x, 1 and 0. We find 1 is larger. 1 and 2, we find 2 is larger. So the LCM for the variables is simply xy squared, as we found over here. So there's two ways to do this here, and pick which works for you. After a while, you can do this the way we do the numbers. (51) x plus 1. Now this is a different kind of example, but I want to remind people that x is prime and x plus 1 is also prime. And they're prime because they are both not factorable. We can't factor them. That's what makes them prime. So this question is a lot like, I'm going to say, recall. When they asked you for the LCM of both x and y, this is kind of thinking this as a different term, even though it involves x, or a different prime. Symbolically, we can replace y with x plus 1. And remember, when there is no prime that divides these, the LCM here was, again, the product of those two. So just like before, we can say the LCM, since they're both different primes, is x times x plus 1. So this here is how we can think of it, which is analogous to having the answer xy. So remember, we had that kind of question in the past, and this is why that question was very valuable here. So put a star here because that shows up quite often. You can have, and just say as a note, that often shows up, they can give you x minus 1 and x plus 1. And you again notice that these two are primes. So that means the LCM will be the product. X minus 1, x plus 1. That's your LCM. Since they're both prime. You can have x plus 6, x minus 7. You can have x plus 5, x minus 3, x plus 4, x minus 4, 2x plus 3, 3x plus 2, x minus 8, x plus 8. This example is analogous because in every case you're given a pair of primes here. X plus 5 and x minus 3 are prime. They're not factorable. X plus 6, x minus 7 is prime. They're both not factorable. X plus 4 and x minus 4 are prime. They're both not factorable. 2x plus 3, 3x plus 2 are both prime. They're both not factorable. X minus 8, x plus 9 are both prime. They're both not factorable. They can give you x, x minus 8, y, y plus 7. Again, both prime, both not factorable. And in each case, the LCM is simply the product. Make sure you put parentheses. Again, LCM is just the product when they give you a pair of primes. Let's see if this shows up again. This is 51. (53) X plus 1, x minus 1. Again, you have a pair of primes. If you want, you can say, here's a prime, here's a prime, you got a pair. LCM is the product. Happened to be our first note. Thought it looked familiar. (55) X minus 1, x minus 4. Again, they gave us a pair of primes. LCM is x minus 1, x minus 4. First prime, second prime, LCM is the product. X plus 6. A pair of primes. Both of these terms are prime. The LCM is the product. First prime, second prime, they're not factorable. LCM is the product. Multiply them too. (10x) 25x squared. Numbers separate from the variables. LCM of 10, we have to find a prime that goes into both. 5 goes into 10 twice. 5 goes into 25 5 times. We need a prime that goes into both of these two numbers. There is none, so we're done. The LCM would be 5 times 2 times 5, or the LCM will be 50. Again, for the variables, it's x to the largest power. 1, 2. 2 is larger. So my LCM is going to be 50 x squared. 50 for the numbers, x squared for the variables. Final answer. Here's your LCM. (61) x minus 1. We're given a pair of primes. So the LCM is going to be the product. First prime, second prime, multiply them, there's your LCM. (63) 4x 8 x minus 1. We're going to do them separate. Numbers separate from the variables. 4 and 8. I need a prime that goes into both of these. 2 goes into 4 twice. 2 goes into 8 4 times. Prime that goes into both. 2 goes into 2 once. 2 goes into 4 twice. There are no other primes that go into both of these numbers. So my LCM is the product. 2 times 2, 1 times 2, or simply 8. Now for the variables, we notice x and x minus 1. Again, for the variables, they've given us 2 primes. So for the variables, the LCM will be x times x minus 1. So for the final answer now, LCM will be 8 times x minus 1. For the numbers, it's 8. For the variables, it's x times x minus 1 because they gave us, again, a pair of prime terms. They're not factorable. LCM is 8x times x minus 1. (65) 12 x plus 4. 15 x minus 4. We're going to do them separate. 12 and 15, and then x plus 4 and x minus 4. So for the numbers 12, 15, we need a prime that goes into both. 2 goes into 12 6 times, but 2 does not go into 15. So that's not our prime. 3 goes into 12 4 times, and 3 goes into 15 5 times. So again, we need a prime that goes into both of these numbers, and we find that there isn't any. So my LCM here is going to be 3 times 4 times 5, or 60 is the LCM. Now, for the variables here, it's going to be x plus 4 times x minus 4 in parentheses. Now again, the reason being is x plus 4 is prime, as x minus 4 a different prime. The LCM, when you have a pair of primes, again, is simply the product. This is why we have x plus 4 times x minus 4. But the LCM for the numbers was 60. So as a final answer, LCM will be 60 times x plus 4 times x minus 4. This is your final answer. (67) x squared minus 4, x squared plus 7x plus 10. Now for this question here, we have to factor. So when we factor, we end up with, since this is the first one is the difference of perfect squares, we have x plus 2 times x minus 2. The second trinomial is factored as x plus 2 times x plus 5. So we're going to have to figure out the LCM here. Now, I'm going to let you guys know, again, we can look at this as, maybe you look at the variable here for x plus 2 as simply a y. So this is the same x plus 2. So you have y and y here. And x minus 2, we're going to let be possibly w, since it's a different term. And then x plus 5 is even different, so there's 3 terms here that are different. We're going to call that z. Now, the reason I do this here is so that you guys can identify how you might want to proceed here for finding the LCM. So if you said I got yw and yz, remember, here's my y, here's w, and here's the z. So by the technique that we've been using, we need a prime that goes into both of these. We can clearly see that y goes into both. That y, w divided by y is w, so we're going to bring that down. And then yz divided by y is z, so we're going to bring this down. Remember, x plus 2 is y, x minus 2 is w, x plus 5 is z. So this makes things a lot easier now. I try to find another prime with these variables that goes into both. I find that there is none. So here's my LCM now. Y, w, z. However, that's not what we were given. So the LCM here is going to be now. Y is represented by, or I should say x plus 2 is represented by the y right here. W is represented by, or x minus 2 is represented by the w. They're the same things. X plus 5 is represented by z. So here, my final answer here, this product is the LCM. Because the LCM for the single variables is right here. So here's a way we could deduce the answer. And that's number 67. 69, x minus 1 squared, x squared minus 1. Again, we factor because this is already factored. We have the difference of perfect squares, x plus 1 times x minus 1. So if we look at the details here, we're comparing x minus 1 squared with x plus 1 times x minus 1. Now, I'm going to switch the order here because the order in which you multiply doesn't matter. So I'm going to call this x minus 1 times x plus 1. Now we're going to see why we do this. If I change my variables again, like I did before, and maybe I call my x minus 1 term y, that gives me y squared. This is y here, and it's to the second power. This is y, so I can put that there as well. So y squared, y, and maybe I'll call this x plus 1 term z. So I got yz here. So I'm just changing here the variables here, so that when I go through my procedure, y squared, yz, I need a prime that divides both of these, with a 0 remainder, of course. The prime y goes into y squared. Our y squared over y is 1, y squared divided by y. And then yz, this is what we're doing. Y squared over y is y, and yz over y is z. So we bring down those quotients here. And then we try to find a prime that goes into both of these numbers, and we find that there is none. So that my LCM here will be y times z, or simply y squared z. However, they didn't give us terms that involve the letters y and z. We have to go back and remember that y is really x minus 1. So my LCM here with y squared is going to be now x minus 1 squared. And then the z term is here. It's x plus 1. So my LCM is the product here of these two terms. And we're done.